Welcome to Rivera Institute of Mathematical Sciences. Today we are discussing Part B questions of linear algebra from CSIR June 2020 exam conducted on November 26. There is total 6 number of questions from Part B. Okay, first one. Let capital A and capital B be 2 by 2 matrices, then which of the following is true? Okay, for this problem, it is easy to find the option by eliminating the wrong options. For that, here I consider capital A is the 2 by 2 identity matrix, that is 1 0 0 1, and capital B is also 1 0 0 1. And what is A plus B? A plus B equal to 1 plus 1 is 2, that is 2 0 0 2, and A minus B is the 0 matrix, that is identity minus identity, which is 0 matrix. And what are the determinants of these four matrices? Here, determinant of A is the identity matrix, therefore determinant of A equal to 1. Similarly, determinant of B is also equal to 1. And what is determinant of A plus B? Determinant of A plus B equal to 2 into 2, that is 4, and A minus B is the 0 matrix, therefore determinant of A minus B equal to 0. Okay, now consider the four options. First consider option A. Okay, what is determinant of A plus B? That is LHS equal to determinant of A plus B plus determinant of A minus B. Here determinant of A plus B is 4, therefore 4 plus 0 equal to 4. 4 plus 0 equal to 4. And what is the RHS? RHS equal to determinant of A plus determinant of B. Here determinant of A equal to 1 and determinant of B is also 1, therefore 1 plus 1, which is equal to 2. Both are not equal, therefore option A is wrong. Now consider option B. Here determinant of A plus B, LHS equal to determinant of A plus determinant of A plus B plus determinant of A minus B, that is 4 plus 0 equal to 4. And what is RHS? RHS equal to 2 times determinant of A minus 2 times determinant of B, that is 2 into 1 minus 2 into 1, which is equal to 0. Both are not equal, therefore option B is also false. Now consider option D. Option D, determinant of A plus B minus determinant of A minus B, that is determinant of LHS equal to determinant of A plus B minus determinant of A minus B, that is 4 minus 0, which is equal to 4, and RHS equal to determinant of A plus determinant of B, that is 1 plus 1, which is equal to 2. Both are not equal, therefore option D is also false. And here option C satisfies these two matrices, and there is only one option is true because this is a part B question, therefore option C is true. Okay, next one. If capital A equal to 3 minus 2 2 minus 1, then the value of A raised to 20 is. Here given that capital A equal to 3 minus 2 2 minus 1. Okay, we can write this A as identity matrix plus some other matrix, that is 2 minus 2 2 minus 2. Here 2 plus 1 is 3, minus 2 plus 0 is minus 2, 2 plus 0 is 2, minus 2 plus 1 is minus 1, that is capital A can be written as identity matrix plus B. Okay, now consider the matrix capital B. What is B? B equal to 2 minus 2 2 minus 2. Here each row sum of B is 0, that is 2 minus 2 equal to 0, 2 minus 2 equal to 0. So 0 is an eigenvalue of this matrix. 0 is an eigenvalue of B. And we know that trace of a matrix is the sum of the eigenvalues. Trace equal to sum of eigenvalues. What is trace of this matrix? 2 minus 2, that is 0, that is 0 equal to sum of eigenvalues. One eigenvalue is 0 and the remaining eigenvalue is B, that is B plus 0 equal to B, that implies B equal to 0. So we get the two eigenvalues of this matrix is 0. For a 2 by 2, for an n by n matrix, all its eigenvalues are 0, implies that is a nilpotent matrix. So here it is a 2 by 2 matrix and all the eigenvalues are 0, so it is a 2 by 2 nilpotent matrix. And we know that for a 2 by 2 nilpotent matrix, B square must be 0. If B square is equal to 0, then B cube equal to 0, B etc. up to B raised to any power equal to 0. Now we have to find the value of A raised to 20. Okay, what is A raised to 20? A raised to 20 equal to A is nothing but identity plus B. identity plus b all raised to 20. And we know that the binomial expansion a plus b all raised to 20 equal to a raised to 20 plus 20 c1 into a raised to 19b plus 20 c2 into a raised to 18 into b square plus etc. up to b raised to 20, right? So here identity plus b all raised to 20 equal to identity raised to 20 plus 20 c1 into identity raised to 19 into b plus 20 c2 into identity raised to 18 into b square plus etc. up to b raised to 20. We know that b is a nilpotent matrix, 2 by 2 nilpotent matrix, therefore b square equal to 0, b cube equal to 0, etc. up to b raised to any power equal to 0. So all these term will vanishes. That is, this will become identity raised to 20. What is identity raised to 20? It is identity itself, that is 1001 plus 27 is 20 into identity raised to 19 into b is b itself, that is 20 into 2 minus 2, 2 minus 2. So this will become 1001 plus 20 into 2 40 minus 40, 40 minus 40. So this will become 1 plus 40, that is 41 minus 40, 40 minus 39. That is option, which option is true? Option b is true. Okay, let capital A be an n by n matrix such that the set of all its non-zero eigenvalues has exactly r elements, then which of the following is true? Okay, for that here I consider a matrix capital A equal to 0 1 0 0. Here this is an upper triangular matrix with all its diagonal entries are 0, and we know that an upper triangular matrix with all its diagonal entries are 0 is a nilpotent matrix, and all the eigenvalues of a nilpotent matrix are 0. So here r equal to 0. What is r? R is total number of non-zero eigenvalues of that matrix. So here r equal to 0, and what is the rank of this matrix? Rank of this matrix equal to 1. Okay, now consider the four options. For the first option, what is rank of a? Rank of a equal to 1, and here r equal to 0, and given that rank of a is less than or equal to r, that is 1 less than or equal to 0, it is not possible, therefore option a is false. Now consider option b. If r equal to 0, here r equal to 0, then rank of a is less than n minus 1. Here rank of a equal to 1, and here I choose capital A is a 2 by 2 matrix, therefore n minus 1 equal to 2 minus 1 equal to 1. 1 less than 1, it is not possible, therefore option B is also false. Now consider option D. Okay, a square has r distinct non-zero eigenvalues. For that I consider a matrix capital A equal to 1 0 0 minus 1. This is a diagonal matrix, so its eigenvalues are diagonal entries. What are the eigenvalues of this matrix? The eigenvalues of this matrix are 1 and minus 1. That implies r equal to 2. R is the total number of non-zero eigenvalues, so here r equal to 2. And what are the eigenvalues of a square? The eigenvalues of a square are 1 square, that is 1, and minus 1 square, which is also 1. That is total number of distinct eigenvalue. Here only 1 is the eigenvalue, therefore a square has r distinct non-zero eigenvalues is wrong, therefore option D is also wrong. So here only option C is true. And how can we prove option C is true? Okay, for that here given that the r is the total number of non-zero eigenvalues, that is number of non-zero eigenvalues equal to r. Okay, for an n by n matrix it contains total n eigenvalues, right? So total number of, what is the total number of zero eigenvalue? Number of number of zero eigenvalue. Number of zero eigenvalue equal to, we know that number of zero eigenvalue equal to total number of eigenvalues minus number of non-zero eigenvalues. Here number of non-zero eigenvalues equal to r, therefore total number of zero eigenvalue equal to n minus r. What is number of zero eigenvalue? It is nothing but algebraic multiplicity of 0. That is algebraic multiplicity of 0 equal to n minus r. And we know that geometric multiplicity of an eigenvalue is always less than or equal to algebraic multiplicity of that eigenvalue, right? So geometric multiplicity of 0 is less than or equal to algebraic multiplicity of 0. And what is algebraic multiplicity of 0? It is n minus r. That implies geometric multiplicity of 0 is less than or equal to n minus r. And what is geometric multiplicity of 0? It is nothing but nullity of that matrix. That is nullity of A is always less than or equal to n minus r. Okay, now consider, we know that by rank nullity theorem, rank of A plus nullity of A equal to n. That implies rank of A equal to n minus nullity of A. Okay, here nullity of A is less than or equal to n minus r. That implies minus nullity of A is greater than or equal to minus of n minus r. That implies minus nullity of A is greater than or equal to r minus n. That is rank of A equal to n minus nullity of A. That implies rank of A is greater than or equal to n plus r minus n. That is rank of A is greater than or equal to r. Therefore option C is true. Okay. Next question, let capital Q be a real quadratic form on R2, then which of the following is positive definite? Here capital Q is a real quadratic form on R2. So the corresponding matrix of this quadratic form will be a 2 by 2 matrix. First consider a quadratic form on R2, that is a x square plus b y square plus 2c xy. This is a quadratic form on R2, and the matrix corresponding to this quadratic form is capital A equal to A C C B, right? And this quadratic form is positive definite if the leading principal minors are greater than 0. What are the leading principal minors of this matrix? The leading principal minor of order 1, that is D11 equal to the first entry, that is A, and leading principal minor of order 2 is D22, which is equal to the determinant of the given matrix, that is AB minus C square. If both these leading principal minors are greater than 0, then the given quadratic form is positive definite. Okay, now consider the four options. Here I consider option A. What is the matrix corresponding to this quadratic form? A equal to 0, 1 by 2, 1 by 2, 0. Okay, now what is D11? D11 equal to 0, which is not greater than 0. Therefore this quadratic form is not positive definite. Now consider option B. What is the matrix corresponding to this option? Capital A equal to 1 minus 1 by 2 minus 1 by 2 1. Now what is D11? D11 equal to 1 and D22 equal to determinant of this matrix, that is 1 minus 1 by 4, which is equal to 4 minus 1, that is 3 by 4. Here both the leading principal minors are greater than 0. So this quadratic form is positive definite. Now consider option C. What is the matrix corresponding to this option? Capital A equal to 1, 1, 1, 1. That is each entries are 1. Now what is D11? D11 equal to 1, which is greater than 0, and D22 equal to determinant of this matrix, which is 0, which is not greater than 0. Therefore this quadratic form is not positive definite. Now consider option C. What is the matrix corresponding to this option? Capital A equal to 1, 0, 1 by 2, 1 by 2, and D11. D11 equal to 1, which is greater than 0, and D22 equal to 1 into 0, that is 0 minus 1 by 4, which is less than 0. So this quadratic form is not positive definite. Therefore only option B is true. Okay. Next one. Let capital A be a 2 by 2 matrix with a determinant of A equal to 1 and trace of A equal to 3. Find the value of trace of A square. Here the matrix is a 2 by 2 matrix, and we know that the sum of eigenvalues is the trace and the product of eigenvalue is the determinant. Here lambda 1 and lambda 2 are the eigenvalues of this matrix. That is, here capital A is a 2 by 2 matrix, so the eigenvalues are lambda 1 and lambda 2, and we know that the sum of the eigenvalue is trace. That is, lambda 1 plus lambda 2 equal to trace of the given matrix is 3, and product of the eigenvalues are determinant. That is, lambda 1 into lambda 2 equal to 1. Now what are the eigenvalues of A square? We know that if lambda 1 and lambda 2 are eigenvalues of A, then eigenvalues of A square is lambda 1 square and lambda 2 square. And what is the trace of A square? Trace of a matrix is sum of eigenvalues. Therefore trace of A square equal to lambda 1 square plus lambda 2 square. Okay, now consider lambda 1 plus lambda 2 whole square. Okay, what is lambda 1 plus lambda 2 the whole square? Which is equal to lambda 1 square plus 2 times lambda 1 lambda 2 plus lambda 2 square. Okay, and what is lambda 1 plus lambda 2? Lambda 1 plus lambda 2 is 3. That is, 3 square equal to lambda 1 square plus 2 times lambda 1 into lambda 2 is 1. 2 into 1 plus lambda 2 square. That implies 9 minus 2 equal to lambda 1 square plus lambda 2 square, which is equal to 7. That is, lambda 1 square plus lambda 2 square equal to 7. That is, trace of A square equal to lambda 1 square plus lambda 2 square, which is 7. Therefore option D is true. Okay. Next one, for AB belongs to R, let P of xy equal to A square x1 y1 plus AB x2 y1 plus AB x1 y2 plus B square x2 y2, where x equal to x1 x2 and y equal to y1 y2 belongs to R2. For what values of A and B does P from R2 to R define an inner product? Okay, here we have to find the values of A and B for which P is an inner product or not. So first consider the inner product x comma y equal to x transpose. Here it is of matrix form, therefore x transpose A y. That is, x1 x2 into some matrix capital A into y1 y2. Now we have to find the coefficients of this matrix capital A. So what is the first coefficient? That is the entry corresponding to the first one. Here first entry is the coefficient corresponding to x1 y1, that is A square, and the second entry is the coefficient corresponding to x1 y2, that is nothing but AB. Similarly, the third entry is the coefficient corresponding to x2 y1, that is also AB, and the last entry is the coefficient corresponding to x2 into y2, that is B square. So here the matrix capital A is A square AB AB B square. This matrix is a symmetric matrix, so we have to check the given matrix is positive definite or not. That is, we know that a matrix is inner product if it must be a positive definite matrix. So what are the conditions for a matrix to be positive definite? That is, the leading principal minors must be greater than 0. And what are the leading principal minors of a 2 by 2 matrix? The first leading principal minor, that is leading principal minor of order 1, is the first entry of that matrix. That is, D11 equal to A square. A square is always greater than 0 if A not equal to 0. So first leading principal minor is greater than 0 if A not equal to 0. And what is the second leading principal minor of a 2 by 2 matrix? It is nothing but the determinant of that matrix. That is, A square B square minus AB into AB, which is equal to A square B square minus A square B square, which is always equal to 0. So the leading principal minor of order 2 is 0 and it is not greater than 0. So the given matrix is not a positive definite matrix. So for any values of A and B, this is not an inner product. So option D is true, right?